In this section, we're going to look at applications using trig, log, and exponential functions. So when we say applications, we mean some of the applications that we saw in chapter 24, including things like Newton's method, linearization, related rates. So it will give us a chance to go back over those application type problems, but with new functions and practice the derivatives of trig, log, and exponential functions along the way. So here's our first problem. We're going to solve the equation e to the x plus ln of x squared plus 5 minus 4 equals 0 in the interval where x ranges from 0 to 1. So first thing is to recognize the type of problem this is. This is a Newton's method problem. And if you want to refer back to Newton's method, we saw that in section 24.2. So Newton's method allows us to solve an equation of the form f of x equals 0. So all this stuff on the left side here, that's going to be our f of x. It allows us to find an approximate solution. And we're told in the problem that the x value that we're looking for is somewhere between 0 and 1. So our first step here is going to be to figure out what a good starting x value is. We'll just make a little table of values here. And what we're looking for is for the value of our function to be close to 0. So let's say we want f of x to be approximately 0, where we're just saying f of x is the left side of this equation. So let's try plugging in here. We'll plug in the x value 0, we'll plug in the x value 1, and we'll just figure out which one of those is a better starting point. So plugging in to this function here, if you were subbing in 0, you'd go e to the 0 plus ln of 5 minus 4. That comes out to about negative 1.39. And if you did the same thing with x equal 1, comes out to about 0.51. So if we look at these two f of x values, the one that's closer to 0 is this one. Therefore, our starting x value is going to be 1. So let's say use x0 equals 1. So now in a minute, we're going to make a table of values to help us figure out our solution. But before we can do that, we're going to need to know the derivative of our function. So maybe just for the sake of keeping everything organized, I'm going to write out f of x again, and then we can think about taking the derivative. So f of x was just the left side of our equation. It was e to the x plus ln of x squared plus 5 minus 4. And let's think about taking the derivative of this. Okay, so to differentiate an exponential function, you'd go ln of e, which is 1, times your exponential, times the derivative of the exponent, which is just going to be 1. So you just get e to the x there. Plus, now we're going to practice taking the derivative of a logarithmic function. The base is e when you're working with ln. So you'd have 1 over ln e, which is just 1. Then you go 1 over your function, and multiply by the derivative of the inside function. So most natural way to write that would just be 2x over x squared plus 5. Let's do that, 2x over x squared plus 5. And then the minus 4 goes away when we take our derivative. So there's our f prime of x. Great, so with that, we've got our starting x value. We know what our function and our derivative is, so we can build our table of values. So you may remember from Newton's method, in the first column, you put your x value. In the second column, you put your f of x value. And I'm going to write specifically what we're plugging into. So it's e to the x plus ln of x squared plus 5 minus 4. That's going to be our second column. Third column comes from your derivative. So that'll be e to the x plus 2x over x squared plus 5. And then in the last column, that's where you build your x value for the next step. So you go x value minus your function value divided by your derivative value. You may remember that formula from Newton's method. So that's how you get your x value for the next step. And with that, we're ready to start. So we said, based on our table of values, that we're going to use 1 as our starting point. So we're going to plug 1 in here, and then we're going to plug that into our function. Let's write everything down to 4 decimal places. So if you plug x equal 1 into your function, you would get 0.5100. And if you plug 1 into this derivative, so if you went e to the 1 plus 2 over 6, that would give you 3.0516. So then for our last step in this line, we're going to take our x value and go minus our function, so 0.51 divided by 3.0516. So that's what we're doing, but I'm just going to write down the result. And again, we'll write everything down to 4 decimal places. So that comes out to 0.8329. We're going to take this value, and that's going to be our x value for the next step. So you just bring this over here and start the process over again. So 0.8329. Okay, let's try another step here. So taking our 0.8329, putting into our function, you can check that you get 0.0393. And you can also check that when you take your 0.8329 and put it into your derivative, you get 2.5925. That's what it would look like when you put it into your calculator. And we can just work out what that is to 4 decimal places. So that comes out to 0.8177. So now here's the part of the problem where we decide whether we're done or not. Our final answer is going to be reported to 2 decimal places. So you can look at your first step here, and let's just round off. What would our answer be if we had rounded that off to 2 decimal places? I'll just put that in brackets on the side. That would be 0.83. And if we had done the same thing after the second step, we would have 0.82. So the idea is that after every step, we're getting closer and closer to the solution. But at this point, we don't know whether the solution is closer to 0.83 or closer to 0.82. So we're going to do one more step. And if we get 0.82 again, then we know that's our answer. So once you get the same value rounded to 2 decimal places twice in a row, then you're done. So let's try it. I'm pretty sure we're going to finish up in this next step. So let's take 0.8177, plug it into our function. You get 0.0002. So what I would encourage you to check at least some of these values on your calculator. Make sure you're comfortable plugging it. Let's take 0.8177, put it into our derivative. So that's 2.5538. And then finally, for our last step, the way we get our next x value is we take our current x value and subtract off the value of the function divided by the value of the derivative. So that would look like that. And if we put that into our calculator to 4 decimal places, that comes out to 0.8176. So that definitely rounds to 0.82. And since we've got the same number to 2 decimal places twice in a row, we are done. So our answer to the problem is just x is approximately 0.82. Remember, the general rule is that you always carry 2 extra decimal places in your intermediate calculations. So you can see that everything in the table is being done to 4 decimal places. Then we give our final answer to 2 decimal places. So there we go. We found an approximate solution to that original equation, which we've got right up at the top of the screen here. Here's our next problem. A particle has a given position. We know the x-coordinate in terms of time and the y-coordinate in terms of time. We want to find its velocity at t equal 1. So this type of problem comes from our section on curvilinear motion. If you want to look back at that, that was section 24.3. And let's remember how we go about finding velocity. So the idea is that we're going to find the velocity in the x direction, or you could call that horizontal velocity, and we'll also figure out the vertical velocity. And then once we've got both of those, then we'll put those together and figure out our overall speed and direction. So the way we find v sub x here, the horizontal velocity, is we're just going to take the derivative of the x position with respect to time. So derivative of position with respect to time is what's going to give you your speed or your velocity. All right, so let's figure that out. We have to take the derivative of a function that is log base 2 of something. So according to our derivative rules, we're going to go 1 over ln 2 times 1 over the inside function times the derivative of the inside function. So 1 over ln 2, because the base of our logarithm was 2, go 1 over your inside function times derivative of your inside function. So that's our v sub x. And then the idea is that we're looking for the velocity at t equal 1. So we might as well do this extra step here and just say at time 1, what have we actually got? So this would look like 3 over 7 ln 2 would be the easiest way to write that. And we can actually round that off to 4 decimal places just so we've got a numerical value to work with. So 3 over 7 ln 2 works out to about 0.6183. So let's do the same thing for the vertical velocity. I'll just space this out a little bit more. So to get our vertical velocity, we're going to go dy by dt. So that's just the derivative of your vertical position with respect to time. Okay, let's scroll up so we can see that. So y is the function 3 to the sine t. Okay, so that's an exponential function. It's got a constant base and it's got a variable in the exponent. So let's think about how we take derivatives. We go line of the base times the exponential function times the derivative of whatever's in the exponent. So derivative of sine t is cos t. And then we want to do the same thing here where we figure out the value at t equal 1. So I might just put the numerical value portion in a box just so that we keep the process organized. Okay, so we did both our derivatives and now we're going to plug in at t equal 1. So at t equal 1, this would look like ln 3 times 3 to the power sine 1 times cos 1. And since we're dealing with trig functions here, it's important that our calculator's in radian mode so that the calculator understands we're putting 1 radian into the trig function. We're not putting 1 degree into the trig function. It's 1 radian, so radian mode required. Okay, so if you just type that into your calculator, ln 3 times 3 to the sine 1, you might want brackets around the sine 1 there. Most calculators could probably figure that out, but just to be safe, let's bracket that. And let's get a numerical value here. We'll do this to 4 decimal places. So it comes out to about 1.4961. So there we go. We've got our horizontal speed or our horizontal velocity and our vertical velocity. And we're going to now put these two numbers together to give an overall speed and direction for our particle. So let's think about the speed first because that's the easier part. If you want, you could just draw sort of a generic picture here. So you've got some horizontal velocity, you've got some vertical velocity, and if you put those together, that gives you a right triangle. You could call this, the length of the hypotenuse here could be your speed, and you could just think about your speeds in the horizontal and vertical direction. So according to the Pythagorean theorem, you'd say v is the square root of vx squared plus vy squared. Okay, so let's take the square root of our 0.6183 squared plus our 1.4961 squared. Just bracket around that for the sake of the calculator. And we can just drop a couple of decimal places here. So let's say for our speed, let's just give 2 sig figs. Let's say 1.6 meters per second for our speed. So we've carried a bunch of extra decimal places in our intermediate calculation. So last thing we need to do is think about the angle. So again, I'm going to draw a little picture here. So imagine you've got this triangle. You got your v sub x, your v sub y, got your v there, and we're trying to figure out this angle here, the direction in which our particle is moving. So you could say, well, theta would be arctan of v sub y over v sub x. That's because tan of theta is the opposite over the adjacent. So tan of theta would be vy over vx, and then you could just solve for theta there by saying theta is arctan of your vy over your vx. But the issue is that this only works actually if our angle is in quadrant 1 or quadrant 4. If our angle is actually over on the left side of the diagram, then we need to add 180 degrees to this. So let's say plus 180 degrees, question mark. And the way you figure out whether you need to add 180 degrees is you just figure out what quadrant you're in. So let's look back at our values here. This is where these numbers come into play. So our horizontal velocity is positive. Our vertical velocity is positive. So that tells us if we were to draw, let's say, just a vector representing those numbers, our velocity would be doing something like that. I'm going to say we're about 0.6 in terms of the horizontal velocity, and we're about 1.5 in terms of the vertical velocity, just to round those numbers off a bit. So that angle's in the first quadrant, and that means there's no correction required here. If you were somewhere over in quadrant 2 or in quadrant 3, then you would need to add 180 degrees to get the correct angle. Okay, so we're ready to finish up and get our angle here. So we're going arctan of our v sub y was 1.4961 and our v sub x 0.6183. No correction required there. We don't need to add 180 degrees. You can put your calculator into degree mode, and that comes out to about 68 degrees. So just to give a nice answer at the end of the problem, the question was to find the velocity. So you can say the velocity is, we said it's 1.6 meters per second at 68 degrees, and we're done. So here's our next problem. A toy helicopter rises vertically at a constant 3 meters per second. How fast is theta changing when the height is 12 meters? So we've got a picture that comes along with this problem. We need the picture just because that's where the angle theta is identified. And we know that the angle is being measured from a distance that's 10 meters horizontally away from the position of our helicopter. So this problem is a related rates problem. If you want to look back at related rates, that was section 24.4 that we covered that. It's a related rate because we have a sense of how fast the helicopter is rising. And so based on that rate, we want to find the related rate of how fast is the angle changing. So first thing we should do is just to introduce a variable. Let's redraw the diagram, just the important pieces of the diagram here. So we've got our angle theta. We know this horizontal distance is 10. We know the vertical distance is changing over the course of the problem. So maybe let's call that h, or you might want to call it y. So let's call that the height of the helicopter. And we know that that height is changing at a rate of 3 meters per second. So that is dh by dt, the rate of change of the height with respect to time. It's positive because we're told that the helicopter is rising. What we want to find is the rate of change of theta. So that's d theta by dt. That's what we want to know when the height is 12 meters. Okay, so h equal 12 at the point that we're interested in. So if we think about the steps that we went through for a related rates problem, we said step 0 was just pulling the information out of the problem. So we've done that. We've got this right triangle. We've got all our pieces of information pulled out, and therefore we don't need to look back at the problem anymore. And then the first main step was getting an equation that would relate our variables together. So we need some equation that relates h and theta together. Well, you could think about taking the tangent of theta. You could say tan theta is equal to opposite over adjacent, so that would be h over 10. Maybe even better, because down the line we're going to have to be taking derivatives of this. Even better would be to say theta equals arctan of h over 10. I would say that's slightly better because then we've got theta isolated on the left side. It's just slightly easier to take the derivative. So let's go with that. So that's an equation that relates theta and h to one another. And then based on that, in step 2, we're going to take derivatives with respect to time. So take d by dt of both sides of the equation. Okay, well on the left side, we're going to have d theta by dt. And on the right side, we're going to have a chain rule. The reason we're going to have a chain rule is because this right side here does not depend on t. Right now, it depends on h. So what we really want to say is to get d theta by dt, we're going to have to think about what is the derivative of theta with respect to h. And then once we know that, we can multiply that by dh by dt. So just on an intuitive level, you can imagine the dh's canceling out, and that would convince you, yeah, it is valid to write down this equation. And then the reason why you want to write down that equation is because our formula for theta actually involves h. So we would go about taking the derivative of theta with respect to h first, and then we would just multiply by this dh by dt. This thing is actually just a number. It's the rate at which the helicopter is rising. d theta by dt, which is what we're ultimately trying to find, is equal to, well, let's figure out this d theta by dh. So we're going to look up at the top of the screen here. We're going to take the derivative of this function with respect to h. Okay, so maybe let's do a refresher here. We need to just remember how to take the derivative of the arctan function over on the side. So derivative with respect to x of arctan x, you may remember, is 1 over 1 plus x squared. If you, say, wrote that in terms of h, that would look like d by dh of arctan of h would be 1 over 1 plus h squared. So that's just that same formula, except in this problem we're calling our variable h instead of x. And then the only other difference is that, if you had something like, let's say, arctan of 2h instead of just a single h in there, but a 2h, then all of a sudden we have a chain rule. So you'd have to go 1 over 1 plus your inside function squared, and then times the derivative of your inside function. So this is what we're going to be thinking about in this particular problem, except we don't have arctan of 2h, we have arctan of h over 10. So we'll just figure out how to modify this. Right, so let's come back to this discussion. We've said d theta by dt is going to be d theta by dh times dh by dt. So we're just going to work here on figuring out what this d theta by dh is, and then we'll multiply that by dh by dt. So let's go ahead with figuring out this part. All right, so taking the derivative of the arctan function, we are going to go 1 over 1 plus whatever our inside function squared is, and then times the derivative of the inside function. Well, the derivative of h over 10 is 1 over 10. So that's our derivative done. And then step 3 of a related rates problem is to find any missing values. So this is just where we look back at the beginning of the problem and we see whether we've got everything that we need to answer the problem. So what are we going to need? We're going to need an h value, and we're going to need a dh by dt value. So let's look back up at step 0 where we got everything. We actually have everything we need. We've got h and we've got dh by dt. So we are good. And then we can just go ahead and solve. So we're just looking back at this last step that we've got up at the top of the screen here. We'll plug everything in and we'll get our answer. So d theta by dt is equal to, well, we've got 1 over 1 plus, the h value that we're using in this problem is 12. So 12 over 10, you could call that 1.2 if you want to make life easier. So you'd have 1 over 1 plus 1.2 all squared times 1 over 10. I'm just going to call that 0.1 because it seems easier to type into the calculator. And then times dh by dt, which was 3. Okay, so I don't really need this big square bracket here. For the sake of the calculator, you do want brackets around everything in the denominator there. So if you typed that into your calculator as is, that would give us our correct answer. And that comes out to about 0.12. That is measured in radians per second, because when you think about units, you're thinking about what are my units of theta divided by what are my units for time. So for theta, it's going to be measured in radians, and for time, it's going to be measured in seconds. Incidentally, we know time is in seconds because we're told in the question that the helicopter was rising at 3 meters per second. Okay, so we got 0.12 radians per second. If you want, you could multiply that by 180 degrees over pi. I would say this is optional. And that would take you into degrees per second. So you could say, or that's approximately 7 degrees per second. So for our next problem, we want to figure out for what value of theta is the function 5 sine theta plus 6 cos theta maximized. So this is a type of problem that we would have thought about in our section on maximizing or minimizing functions. And we saw that in section 24.7, just in case you're interested in referring back to that. So if you want to maximize or minimize a function, really what you're looking for is the critical points for your function. So let's think about taking the derivative of our function, and then once we've got that derivative, set it equal to 0. So that's going to give you your critical points. In some cases, you'll find more than one critical point. So I think that will happen in this problem here, and then we'll need to do a bit of extra analysis just to figure out which one is actually the maximum. Maybe one of those will be a max, one will be a min, for example. Some of the problems we saw in 24.7 were actually a bit more complicated than this one, because in some of those problems we had a restriction where we had to actually solve for one of our variables and plug in before solving the problem. But this problem that we're given here is actually pretty nice because it's already given in terms of one variable. There's just theta in here. There's no other variable. So that's actually going to cut down on the amount of work that we have to do in the problem. So let's go about finding critical points. We'll start with finding f prime of theta for our function, and I think I'll just highlight the function so that we can see that clearly. So taking the derivative, we're going to have 5 times cos theta minus 6 times sine theta. Remember, the derivative of cos x is negative sine x. So the derivative of cos theta is negative sine theta. And then we want to go about setting this derivative equal to 0. So that's where we find our critical points. Okay, so let's think about how to set this equal to 0. Well, if you just have 2 terms in an equation, then usually a good strategy is to move one term to each side of the equation, something like that. And then what you could do is you could divide both sides by cos theta, and then a couple of nice things would happen from there. So first thing that would happen is you could say, well, sine theta over cos theta is really just tan theta. So that's great. That's going to be super helpful in terms of solving the problem. And then the other thing you could do is you could just divide both sides by 6. So you could say 5 over 6 is equal to tan theta. All right, so we've almost got our theta value. To completely get theta, you would think about taking arctan of both sides of that equation. Applying arctan to both sides, you'd have arctan of 5, 6 is equal to, on the right side, you just have your theta value. So that's almost true. I'm going to put a question mark for now. The reason we have to be a little bit careful is that arctan is a restricted function. It can only give you angles in quadrant 1 and quadrant 4. So the correct answer is actually to say theta is arctan of 5 over 6, one option, and the other option is that same angle plus 180 degrees. So let me draw a picture just to figure out visually why that should be true. So let's think about our cast rule. There are 2 quadrants in which tan is positive. So if you take any angle in quadrant 1, tan theta is going to be positive. But that's also true in quadrant 3. If you take any angle in quadrant 3, tan theta is going to be positive. So when we take theta equal arctan of 5 over 6, what we're doing is we're finding some angle in quadrant 1. So we're figuring out a theta value that's here, but there's another theta value in quadrant 3, and that theta value happens to be 180 degrees bigger than the first theta value that we found. So from this step here, where we say tan theta equals 5 over 6, the correct thing to do is to recognize that there are going to be 2 different solutions. One of them is going to be sort of the more obvious solution where you say theta equals arctan of 5, 6, but the other one is going to be that angle plus exactly 180 degrees. So I'm going to erase this step here that was incomplete. Well, why don't we just round these angles off into maybe a couple decimal places, and then we can do a final bit of exploration about where our function is actually going to be maximized. Okay, so at this point, we have two possible critical points, or two critical points, I should say, and these are possible relative maximums. So your critical points are not guaranteed to be relative maximums. They could be a relative minimum, or they could be just a point that falls into neither category. So our two critical points, they come out to about 39.8 degrees, and then the other one is exactly 180 degrees bigger than that, so 219.8 degrees. So the way we'll figure out which one is our maximum is we'll just plug in to our function f. So we'll see, what does f look like at 39.8 degrees, and what does it look like at 219.8 degrees? And based on that, we'll be able to figure out the answer to the question. So let's scroll back to the question now. We'll find the original wording here. The question was, for what value of theta is our function maximized? So our answer is going to be a theta value. It's either 39.8 degrees or 219.8 degrees, or I suppose it could be both. So we'll just investigate the values of our function and figure out which one makes it biggest. So I think it'll be a little bit easier to plug in if we just recopy our function. Our original function from the problem was 5 sine theta plus 6 cos theta. So let's make sure that our calculator is in degree mode. And we'll type into our calculator 5 sine 39.8 degrees plus 6 cos 39.8 degrees. And we'll just figure out what that works out to. So that comes out to approximately 7.8. And if you do the same thing for 219.8 degrees, again, making sure your calculator is in degree mode, negative 7.8. Okay, so we're looking for the spot where the function gets as big as possible. We have these two critical points here. And so we're just choosing between these two spots, and we're saying, okay, well, this is the bigger of the f values. 7.8 is bigger than negative 7.8. And then to answer the question, we're really asking what angle causes that to happen. That's theta equal 39.8 degrees. Or I can say theta approximately equal to 39.8 degrees. So that angle, just around 40 degrees, is the angle that makes our function as big as possible. So last problem for this section, we are going to use a linear approximation to estimate the value of sine of 17 pi over 96. Just to comment on the wording first, when we say a linear approximation, this is sometimes called a linearization. So the two terms are interchangeable. We could have equally well said use a linearization to estimate this value. So this is from section 24.8. You may remember we did a section on differentials and linear approximation. So let's remember our linear approximation formula was f of x is approximately f of a plus f prime of a times x minus a. And this is valid for x values near a. Or it's valid anytime x and a are relatively close together. So in other words, you would not want x and a to be, let's say, different orders of magnitude. That would not give you a good approximation. But as long as x and a are relatively close, you get a decent approximation. Just as for a little bit of insight as to where this formula comes from, makes sense on the surface that f of x would be approximately equal to f of a. And then what we're adding on here is a little bit of error. So this error actually comes from thinking about the differential of the function f, and the way you get the differential is you take a derivative and multiply by a small change in your variable, which is represented by x minus a. So that's just a bit of a flashback as to where that formula comes from before we jump into using it. So my first question in solving this type of problem then is, what a value should we use? So let's think of it this way. The x value is the value where we're trying to estimate our function. So x is 17 pi over 96. That's what we're ultimately going to be plugging in here on the left side. The a value that we want is a nice number that's near our x value. So something near 17 pi over 96. And when we say a nice number, we mean something that's going to go nicely into our function f of x being the sine function. So what number, or what angle, we could say, goes nicely into the sine function and is close to 17 pi over 96? Let's think about 16 pi over 96, or alternatively, you could think about 18 pi over 96. If you simplify this fraction 18 over 96, you could turn it into 9 over 48. Okay, that doesn't sound too great. So I quickly ruled that out as being a nice option. But what about 16 pi over 96? 16 actually divides into 96. If you tried to simplify that fraction, 16 over 96 is the same thing as 1 over 6. 16 pi over 96 is actually just pi over 6. And when we write that down, we realize, oh yeah, that's going to work nicely. Pi over 6 is a great angle to put into our sine function. So that'll work really nicely. That's what we consider a nice number, something that makes your function exact. And it's certainly close to 17 pi over 96. So that satisfies both of those criteria. So let's look up at the formula that we've got up at the top of the screen, and we'll just figure out where we're at here with figuring out the different pieces of the puzzle. So x is the messy value that we're going to want to approximate the function at. We'll use that towards the end of the problem. We've identified what our function is. It's a sine function that we're interested in approximating. And we've got an a value. I'm just going to call that pi over 6 so that it's not too cluttered. We've figured out that pi over 6 is the simplified version of that a value. So let's do this to keep our work organized. Let's say our function f of x is sine x, and we'll figure out the value of f of a. We'll figure out our derivative, and we'll figure out the value of the derivative when we plug in a. And that way we'll have all our numbers organized in one place. Okay, so f of a, let's look over here. F of a is sine of pi over 6. That's 1/2. F prime of x, well, if our function is sine x, our derivative is cos x. And then f prime of a is what happens if you plug your number, pi over 6, into the cosine function. You get √3 over 2. And now we've got all the numbers that we need to plug into our linearization formula. So really what we need, I'm going to put all the important stuff in a box. You just need to know your a value, which we've got highlighted here. You need to know your f of a value, and you need to know your f prime of a value. So we're good to go. I think I'll just recopy the linearization formula so that we can see it in front of us. So f of x is approximately f of a plus f prime of a times x minus a. What we're doing specifically here is our function is the sine function. So we're saying sine of x is approximately this number f of a, 1/2, plus √3 over 2 times x minus pi over 6. So we have subbed in a all the way across that formula. The only variable that we've got left in here is x. So this is our linear approximation, or you could also call that our linearization of the sine function. And that's valid for any x value that's near pi over 6. So we're almost done. If we scroll back to the original question, let's just figure out what they were asking. They said, oh yeah, estimate the value of sine 17 pi over 96. So now that we've got our linearization done, the very last step is just to sub in whatever messy x value you're working with, 17 pi over 96, and we'll have our estimate. So we're just plugging in to our last step here. Sine of 17 pi over 96 is going to be approximately equal to 1/2 plus √3 over 2 times 17 pi over 96 minus pi over 6. So we can put this whole right side into our calculator, and that comes out to about 0.5283. So you may remember when we talked about linear approximations in section 24.8, we said really the value of linear approximations in other courses is that it allows you to take a complicated function and simplify it. And that's used a lot when you're doing things like calculating areas and volumes. So this is really a lead into something that would be used in other courses. So that was our review of various applications, and we got some practice along the way of using trig, log, and exponential derivatives. Thanks for watching.